Hi everyone, welcome to lesson 5 of unit 1, which is where we're going to be talking about 18, yes, count them folks, 18 different parent graphs. Some of them you should probably already remember, hopefully, what they look like, and some of them might be new. Okay, so again, beginning from the top, in this lesson we will create a library of functions that are the foundation of our course. You should be able to give a complete analysis for each of the parent functions that include as many of the following as possible. So you should be able to identify the domain and the range. You should be able to identify the roots, y-intercepts, increasing or decreasing behavior, what type of symmetry we have. Is it even or odd, or is there no symmetry? Is there boundedness, local extrema, so a local min or max, horizontal, vertical asymptotes, end behavior, which we're going to use our limit notation when discussing limit or end behavior, and then continuity, whether it's discontinuous and all those different types of discontinuities that are there, or whether it's continuous. Okay, so just a quick refresher. Remember, if we have symmetry to the y-axis, it's going to be an even function. If we have symmetry to the origin, it's going to be an odd function. And if we have symmetry to the x-axis, that makes it not a function. Okay, so that's just a quick review of symmetry characteristics that we have. So now let's go ahead and get ready to go with parent graph number 1. Now this is our probably most basic parent graph, which is a constant. So f of x is equal to some number c. So I'm just going to go down here and put straight line. This one happens to go through 5, but I'm just going to call that y-intercept 0, c. Okay, so it's the function f of x is equal to some constant, right? So the domain of that function is all real numbers. Our range is just whatever that constant is. So it's the set of just whatever c is. So in this specific graph, it would be the set of 5. My range is just always 5, right? What's my end behavior as we approach negative infinity? So as it's approaching negative infinity, it just keeps staying with whatever that constant is, so c. And as it approaches positive infinity, get rid of that line there. As it approaches positive infinity, so going in that direction, again, it's getting closer and closer, or it is always c. Our intercepts, well, we only have a y-intercept, and that will be at 0, c. And then, so what are some other characteristics of this graph? Well, I would say that it's even. It's symmetric to the y-axis. If I were to fold it on the y-axis, it would overlap each other. I would say that it is continuous. I did not have to pick up my pencil or my finger as I was graphing it. Technically, I guess it could be bounded. There's nothing going below or above it, right? And pretty much c is the only number that it is, so there's nothing higher than c or nothing lower than c. All right, so I think we're going to call it good on that one. So that is your constant function. Now moving over to the identity function. So your identity function, my face is over it right now, is the function f of x is equal to x, or y equals x. That has a y-intercept and x-intercept at the origin. And then it has slope of 1. So just the line y equals x is our identity function, right? So 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2. That's all the identities. So negative infinity to infinity is our domain. Our range is negative infinity to infinity. As x approaches negative infinity, what's happening to my graph? It's going smaller and smaller and smaller and smaller, so it's going towards negative infinity. As my graph is getting larger and larger and larger and larger, it's approaching positive infinity. So there's our end behavior. My intercepts, well, I only have one intercept. It's at 0, 0, the origin. And some other information that we have. So let's talk about symmetry. It's not reflecting over the y-axis, but it is reflecting over the origin, so that makes it an odd function. Again, it is continuous. I did not have to pick up my fingertip as I was wrapping it. Okay, there is no boundedness, like it's not bounded above or below because it just keeps going up and it keeps going down, so I'm going to call that unbounded. And let's talk about increasing or decreasing. If we read it from left to right, the graph is definitely increasing the whole entire time. Okay, so that is our identity function. Again, pause this video whenever you need to, because we got a long way to go. Okay, next page. Reciprocal functions are our y is equal to our f of x is equal to 1 over x, right? So those would be our infinite discontinuities, if we remember those. Okay, so let's just do a rough graph of this one. I think we're going to have to scroll this down a little bit so we can get more of the graph. There we go. You guys have the top, right? Yep, we're there. That's good. Okay, so the parent graph of just 1 over x puts a vertical asymptote at 0, right? So let's make our vertical asymptote at 0, dot it through. At 1 over 1 is 1. At negative 1, it'd be negative 1. And then it's going to be kind of like this. And then over here, same thing. I don't know why I'm making those noises. All right, that looks pretty good. We'll go with it. Okay, so what is the domain? Well, the domain is everything excluding, right? Excluding 0. So x cannot equal 0. Do we remember how to put that in interval notation? Well, let's get the left interval first. So we're going from negative infinity to 0, open parenthesis, we're not including it, with the union of, now let's get the right side, 0 to positive infinity. So that's the interval notation for all numbers excluding 0. Looking at our range, again, there's no way to get 0 for our y. It just won't happen, right? Because if I plug in 0 for x, I'm going to get 0 in the denominator. So there's no way to get just 0 over some other number. Or sorry, never mind. There's no way to get 0. Scratch that. I was thinking it was x over x. It's 1 over x. Again, there's no way to make that whole thing 0 because there's a 1 in the numerator. I cannot turn a 1 into a 0, okay? So my range is everything excluding 0 also. So y cannot ever equal 0. So how do we write that in interval notation? Negative infinity to 0, union 0 to infinity. Okay, so now let's talk about the end behavior. So going on the left side of the graph, what is our graph doing? As it keeps going closer and closer and closer to negative infinity, it keeps creeping closer, 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 closer to 0. So the limit of x as it approaches negative infinity of our function is going to be 0. And then the same thing happens on the right side. So as it gets getting closer and closer and closer to positive infinity, our graph keeps getting closer and closer and closer to 0. That's our end behavior on the right. Intercepts, there are none. And so let's go into the other. So here we do have some asymptotes. So my vertical asymptote is the equation x equals 0. My horizontal asymptote is the equation y equals 0. Remember, higher degree is in the bottom than the numerator. It's always y equals 0. We have a discontinuity. What type? We have an infinite, or Ed Gelastic like to call it asymptotic. That's a fancy word. Infinite discontinuity. Continuity. If you just said that was discontinuous, that would be sufficient. That would be substantially enough of an answer. I might be losing it, guys. It's okay. And there's definitely symmetry there. I would say that it's symmetric to the origin, so that would make it odd. Okay, so that is our reciprocal function. Let's move over to our quadratic function. So what does that look like? 0, 0, 1 squared is 1, negative 1 squared is 1, 2 squared is 4, negative 2 squared is 4, 3 squared is 9, that's all the way up there, and then reflect it over here. Did you guys know the trick for quadratic graphs? The slopes are of 1, 3, 5, 7, 9, it's the odd functions. So you go up 1 over 1, and then from there you go up 1, 2, 3 over 1, and then you go up 1, 2, 3, 4, 5 over 1. Yeah? No? Maybe? Anyways, there's your graph. So let's go ahead and graph that. My 9s are probably too high, but that's okay. Alright, so what's my domain? Well, all real numbers. I can put anything in for x. What's my range? Well, it's everything from 0 up, including 0, so inclusive to 0. So square or close bracket on the 0 to infinity. On the left-hand side of my graph, what's my end behavior? Well, it just keeps increasing. So it's going up and up and up and up, so to positive infinity. On the left side of my graph, what's my my right side of my graph, it's going up and up and up and up, so it's going to positive infinity. My intercepts are at 0, 0. So what else do we have? Is it symmetric? Yep, symmetric to the y-axis, so that makes it even. Do we have any boundedness? I could say that it's bounded below. I guess we could have said that the reciprocal graph is unbounded, right? Technically. How about, what about concavity? I would say that that's concave up. Let's talk about increasing and decreasing. So again, if we're reading it from left to right, we are decreasing on the interval negative infinity to 0, right? Negative infinity to 0, we're decreasing. And then we're increasing. And I just realized my face is probably over some of that stuff, so I apologize. Increasing from 0 to positive infinity. And anything else that we can talk about? Nope, I think that's good. All right, shift it down. Yeah, my head's still there. I think I can move my head around. Wow, that's pretty fancy. Sorry, guys, the small things that get me excited. All right, cubic functions. Here we go. What does a cubic graph look like? Cubic graph, 0, 0. 1 to the third is 1. Negative 1 to the third is negative 1. 2 to the third is 8. So 4, 5, 6, maybe somewhere up there. Negative 2 would be negative 8, so maybe somewhere down there. So we got our serpentine looking graph right there. Hopefully yours looks just as fantastic. All right, so our domain is all real numbers. Our range is all real numbers. Let's see, we have the behavior on the left-hand side just keeps decreasing. So going to negative infinity. Behavior on the right side is going up to positive infinity. My intercepts are at 0, 0. That's it. Here we do have a point of inflection. Does everybody see how the point of inflection is also 0, 0? Because if you think about concavity, this kind of is the concave down, but just the left-hand side. And then up here, we have the concave up, but just the right-hand side of it. So that 0, 0 would be a point of inflection. So let's go ahead and talk about that. So we have it being concave down on the interval from negative infinity to 0, or concave up on the interval 0 to infinity. Let's talk about symmetry. Looks like it's symmetric to the origin, so that makes it odd. It's continuous. Did not have to pick up my fingertip when I graphed that. And let's talk about increasing or decreasing. I would say that it's increasing on the whole entire graph, right? If we read it left to right, it's always going up. All right, cool. On to, move my head over here, the square root function. So f of x is equal to the square root of x. What does that graph look like? Well, we're at 0, 0, 1, 1, 4, 2. 0, 0, 1, 1, 4, 2. Doesn't like my finger anymore. Okay, so what's the domain of that graph? Well, we're starting at 0. We can include 0, and we're going to positive infinity. My range, if we read it from bottom to top, again, is going from 0 to positive infinity. I feel like my iPad's going to die soon. Let's plug it in before that happens. Let's talk about the end behavior. Let's see, did I save it? Maybe. I don't know. What's worse? Doorbell's ringing or my iPad dying? I don't know. All right, so left-hand behavior. What's happening to my graph as it goes to the left? It's getting closer and closer, and then it actually approaches 0. So my end behavior on the left. Oh, sorry, I noticed we have it switched. What's happening as we approach 0? So what happens to our function as we approach 0? It's actually going to be 0. So we change that up a little bit. And then on my right behavior, we're going up and up and up and up and up. So we're going to infinity. My intercepts are at 0, 0. Let's talk about symmetry. Do I have any symmetry there? Nope, not symmetric to the y-axis, not symmetric to the origin, so we've got no symmetry. How about, is it continuous? Yeah, it's continuous. No gaps in there or holes. Continuous or jumps. I would say that it's increasing on the whole entire graph. It is concave down. If I poured water in it, it would fall out. So the whole graph is concave down. And we also could say that it's bounded below. I do have a minimum there that nothing's going below. So it's bounded below, an absolute minimum at 0, 0. Okay, so no symmetry, we said that. Maybe we should write that down just so you know that we didn't forget it. No symmetry. Ran out of room. Get that y in there. Okay, so there is your square root parent graph. All right, moving right along. We're chugging away, guys. Here we go. Absolute value. Let's move my head over here. Domain range, what does the graph look like? So absolute value, we should be pros with that, especially since we just put them into piecewise. So 0, 0, 1, 1, 2, 2. So we have the positive version and the negative version. Hopefully yours is actually more accurate than mine. Okay, so 0, 0. So what's my domain? All real numbers. My range is from 0 to infinity. What's happening to my graph on the left side of the behavior? It's going up and up and up and up, so going to positive infinity. On the right side of the graph, it's going up, up, and up, so positive infinity. I have intercepts at 0, 0. Let's talk about symmetry. Symmetric on the y-axis. Yep, so that makes it even. It's continuous. Is it bounded? Bounded below. bound it below. Let's talk about increasing and decreasing. We definitely have two different situations. It's decreasing on the interval -infinity to 0. And then we could say that it's increasing, moving over to this space, on the interval 0 to infinity. And I think that's it. Not concave, so we don't have to do that. Concave up or concave down. It doesn't have a U to it. All right, over to the right. Move my head. Cube root function. What does our cube root function look like? Well, we got cube root of 0 is 0. The cube root of 1 is 1. The cube root of -1 is -1. And then our next nicest cube root probably doesn't occur until x equaling 8. So the cube root of 8 would be 2. So that's probably like right about here. So and then -2 for 8, -8. So maybe right about here. So kind of this graph. All right, so domain, all real numbers. Range, all real numbers. Left behavior is going to -infinity. Right behavior is going to +infinity. Intercept, 0, 0. All right, now let's talk about symmetry. I would definitely say that it's symmetric to the origin, which would make it odd. It's continuous. Do we have any boundedness there? Nope, so I'm going to say it's unbounded. There isn't an absolute max or min. What else? Increasing or decreasing? I'd say it's increasing the whole time. And then we do have some concavity here. Does everybody kind of see the concavity? I would say that we're concave up from -infinity to 0, and we're concave down from 0 to +infinity, which would make what our point of inflection? 0, 0. So point of inflection could be, or would be, 0, 0. So your point of inflection is where the concavity changes. Awesome. All right, cruising right through exponential functions. So what does an exponential function look like? So remember, exponentials is e to the x, e to the 0 is 1, e to the first is like 2.72, something like that. So maybe right about here. So this is the point 1 comma e. And remember that your exponential graph will never be 0 or negative. So you do have a horizontal asymptote at y equals 0. All right, so our domain is all real numbers. Our range is from 0, not including it, so exclusive to 0. Or sorry, hold on, my domain, yeah, my domain's all real numbers, right? Put anything in there. Range 0 to infinity. And then my end behavior, we're getting closer and closer and closer to 0. My right behavior, we're going all the way up to +infinity. My intercepts, I have a y-intercept at 0, 1. There is no x-intercept. Okay. We have a horizontal asymptote at y equals 0. Is there symmetry? No symmetry. Symmetry. Is it continuous? I would say so. Did not pick up my pencil or my fingertip to make that. Is it bounded? Yep, I would say it's bounded below. Bounded below. And I apologize for my chicken scratch, but this is my fingertip writing. And then, is it increasing, decreasing? I would say it's increasing the whole time. And other things to note. we should know that it's the inverse, which we'll talk about inverse functions in a future lesson. It's the inverse function of y equals the natural log of x. E to the x, your exponential function. All right, very good. On to our logarithmic functions. Get rid of that. Slide me over. Okay, logarithmic functions. So that's the inverse. So instead of 0, 1, we have an intercept at 1, 0. Instead of a horizontal asymptote, we have a vertical asymptote. And then instead of at 1, e would be e negative 1. So we're going to have something, or sorry, e1 would be like right here. There we go. Okay, there's my graph. Looks pretty good. My domain in this case, we're going from 0, not including it, to infinity. My range is now all real numbers, so notice how it's the inverse of the exponential function. My behavior as x approaches 0 is going to be that it gets closer and closer and closer and closer and closer to negative infinity because it keeps going down, 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 down. And my right behavior is going to positive infinity. Okay, so it just keeps on going that way. My intercepts, I've got an x-intercept at 1, 0, no y-intercept. So now let's go to the other. Do we have symmetry? Nope. We have a vertical asymptote at x equals 0. It's continuous. I already said that there's no symmetry. Not bounded, right? So unbounded. There's no absolute max or min. This definitely is concave, I would say. Concave down. And then a note here would be that this is so y e to the x is the inverse. So those two are inverses of each other. Okay. Greatest integer function. So your greatest integer function is your most popular step function that we have. So remember what greatest integer means is we're going to the least, so everything's going to be rounding down. So if, I'm just going to write this, don't put anything there. So if we had to do f of 1.5, so your greatest integer of 1.5, so this is the floor one that we were talking about the other day when we were doing piecewise, would go to 1. F of 1 would be 1. F of 1.9 would be 1. So everything's going to round down for greatest integer. So what does that look like as a graph? So we just said that everything from 2, not including 2, to 1 is going to round down to 1. So everything between 1 and 0 will round down to 0. Everything between 0 and negative 1 will round down to negative 1. Between negative 1 and negative 2 will round down to negative 2. Negative 2 to 3 will round down. We can just keep doing that as many times as we want. We can go up this way. So this is your step function, right? Okay, so what's our domain? Well, all real numbers are possible, to go in there. So all real numbers. But now what's our range? Our range is just the integers. It's going to be 1, 2, 3, 4, 5. Do you guys remember the notation for integers? It's this double barred z. Do you guys remember seeing that before? The double barred z. So it's the set of integers. Okay, so what's our end behavior? As we're going to negative infinity, it just keeps going down, 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 down. So it's going to negative infinity. On the right side, it's getting positive, 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 positive. So it's going to positive infinity. What are your intercepts? Notice how all your intercepts occur right in here. in that constant part of the graph. So really, there's an infinite number of intercepts occurring right there. Okay, so it's in the interval of 0 to 1, not including 1, where your intercepts are. That's pretty cool, right? Let's go over here to other. Do we have symmetry? I would say nope, no symmetry. Is it continuous? Definitely not. Discontinuous. But if I had to classify it, we would call that jump discontinuity, right? Are we bounded? Nope. Unbounded. Increasing, decreasing? I would say that it increases on integer values. That's when we see the increase, right? Because it's not increasing on the non-integer values. Good. All right. So, greatest integer function. Questions with that? Alrighty, so now let's go to the signum. This might be something that's new to your life. Maybe you don't know this, but they use this a lot in calculus, the signum function. So the parent graph of the signum function is f of x is equal to the absolute value of x only when x is not equal to 0, and it's equal to 0 when x equals 0. So what does that look like as a graph? Well, the second part would be the origin, right? And then when it's not equal to 0, going to be here, and it's just always going to be 1, because anytime you take the absolute value of itself, divide it by itself, it's going to be positive 1. And anytime you take the absolute value of a negative number divided by itself, it's going to be negative 1. So your graph looks like this. So our domain is all real numbers, because that does give me the option for what happens when it is 0. The range is only these specific numbers, -1, 0, and 1. So we put that in set notation because it's the set of the elements -1, 0, and 1. My end behavior on the left just keeps hovering down there at -1, so it's -1. My end behavior on the right keeps hovering around +1, so it's +1. My intercepts are 0, 0. Do we have symmetry? Nope, no symmetry. Is it continuous? Nope, so discontinuous. Again, this would be a jump if I had to classify it. Do we have boundedness? Yeah, I guess we could say bounded below and above. There's nothing going higher than 1 or -1. Bounded below and above. Let's see what else. I think that's about all we got for that. Okay, so your signum graph, that's a step function. It's another popular step function that's used in calculus. All right, now I just got to get our trig ones in. Here we go. Light at the end of the tunnel. Our sine function, this might be new for some of you. We'll be using trig a lot in this course. So once we get to all the trig work, these are going to become your favorite things to graph, hopefully. Our sine function, when we think about it in 5 key points, we start with an intercept, and then the max, and then we go back to an intercept, and then we go to a min, and then we go back to an intercept. When you think about it graphing, so our first intercept occurs at 0, 0. So on the graph, we're at 0, 0. Okay, and then we have our radians. We calculate trig functions using radians. So that's where the pi over 2 and the pi's and the 3 pi's over 2 come from. So then it pops up to pi over 2, 1 for a max, and then it comes back down to pi, and then down to 3 pi over 2, -1, and then back up to pi. And that is one of the periods. So our period is for a whole length of 2 pi. And then we can just repeat it and keep it going. So here, here, here. Would keep that pattern going, right? And then this would be over here on this side. It would just keep going up like that. Okay, so that is your sine graph. Its domain is all real numbers. Its range is everything between -1 and 1. So it's just going to keep oscillating between -1 and 1. I guess we can put these key points in here. Do you want me to put them in? So our next key point is at pi over 2, 1, and then pi 0, and then 3 pi over 2, comma -1, and then 2 pi 0. So my roots, also known as your X-Intercepts, are occurring at every pi, right? So pi, 2 pi, 0 pi, -1 pi. Which, was I off on that one? I was off on that one, wasn't I, down here? This should be at -1 pi. There we go. So your roots are occurring at all the different pi's. So how do we write that out in notation? So my roots are going to be when x is equal to pi times some number k, where k is in the set, or is an element of the integers. That's my double z. So that kind of looking E is that it's in this element, the set of it, of all integers. That's where your roots occur. And then z double barred is our integers again. It's definitely bounded above and below. It's definitely continuous. Do we have symmetry? Yeah, I would say it's, well, is it all symmetric to, no, I guess it's not all symmetric to the origin because of the going down. All right, sine. Let's go over to cosine. Move my head over here. All right, so sine is just like, or sorry, cosine is just like the sine but shifted over. So now instead of starting with intercept, we're going to start with max intercept, min intercept, back up to max. And our max starts at 0, 1. Then we go to half a pi 0. Then we go to pi -1. Then we go to 3 pi over 2, 0. And then 2 pi comma 1. So what does that look like? So 0, 1, half a pi 0, pi -1, 3/2 pi 0, and then 2 pi +1. So there's our graph. It has a period of 2 pi, and then I can just continue that. So here to there, and so forth, and so forth. So my domain is all real numbers. My range again is -1 to 1. We did our key points, so it's other. We were bounded above and below. It's continuous because it's periodic. It just keeps happening over each period again. And my roots this time are all values of x, when x is equal to half a pi times some number k plus pi k's, right? Where k again has to be an integer. Okay, so that is your cosine graph. Other trig functions we have are tangent and cotangent. So our tangent function is a little bit different because we do have some parts that are undefined here. So when you make your tangent function, we end up with vertical asymptotes. Oops, I'm not writing right now. Oh no. Go away. Oh well, we're just going to keep it blue. I'm already in. I'm committed to it. So we have an asymptote occurring at half a pi. We have an asymptote at 3/2 pi. And then we have it at -½ pi. Okay. So we have intercept here at 0, 0, and then up, and then up. And it kind of looks like a cubic function inside of that. And that just keeps repeating itself inside each period, like such. Okay, and then a little sliver over here. There we go. So my domain gets a little bit funky here because we're undefined at every 1/2 pi, right? So how do we write that out? So x cannot equal every 1/2 pi times some integer plus pi times some integer, where k is in the integers. My range is all real numbers. My period is just pi. And we have a vertical asymptote when x is equal to 1/2 pi plus pi times some number. We'll do k again, where k is in the integers. Let's see, others. It is discontinuous. Unbounded. So we have infinite discontinuity, right? And this is odd. Within the period, right? So it is symmetric to the origin. Okay, my roots are occurring when x is equal to 0 plus pi times some integer. So pretty much at every pi, right, we have an x-intercept. Okay, so that's your tangent graph. Moving to the right, cotangent. So cotangent looks like this. We're just going to shift everything over and flip it a little bit. So now my asymptotes are occurring at 0, pi, 2 pi, -pi. And then at 1/2 pi is where my roots are going to be. And then it's just going to be the inverse of the tangent. Like that. And like this. So there's our cotangent graph. So my domain is everything x cannot equal to pi times k. Again, where k is in the element of integers. My range is still all real numbers. The period is still pi. Now my asymptotes are at x equals plus or minus pi times some number, where our numbers are in the integers. And let's see, others. Discontinuous, infinite discontinuity, continuous, unbounded, no symmetry. We're not symmetric to the origin anymore. My roots are occurring at x equals 1/2 pi plus pi times k, where k is in the set of integers. Good. All right, last two. Here we go. Cosecant function and secants. Now these are fun because you get to like do a skeleton graph and then go from there. Maybe my type of fun is not as much fun as you guys are having. If you made it this far without falling asleep, good job, guys. 18 paragraphs, that's a lot. But we can do it. We will make it through. Okay, so cosecant graphs. So your cosecant graph, the way that you graph this out is you use the sine graph as a skeleton. So remember our sine graph started at 0, 0, came up to 1, went back down at pi, hit the bottom at 3/2, and then there, and then just keep going, like that. Does everybody see it? So now what I'm going to do at every pi, I'm going to make vertical asymptotes, negative pi, there we go. And at 0, missed that pi, 0 is actually a pi too. So your period of pi. And then at each of those bumps, I'm going to create my vertex for a parabola. So it's going to look like this. So that would be your actual graph. So technically I should get rid of my little skeleton dots. There we go. So that is your graph of a cosecant function. So what's that domain? Well, it's x cannot equal every pi times k, where again k is in our integers. Our range is everything except everything between -1 and 1, right? So how do we write that out? So my range is going from -infinity to -1, including it, union +1 to +infinity. My period is 2 pi. Okay, key points, we still do the same thing, integer or intercept max, ignore all that stuff. We got our graph. And then let's see, our asymptotes would be our vertical asymptotes, right? Vertical asymptotes. I'm going to put VA there. VA, vertical asymptotes are occurring at whenever our sine x equals 0. Really, right? So whenever sine of x was at 0, that's when our vertical asymptote is. Are we symmetric to the origin? Yeah, I'd say we're odd. And discontinuous. All right, last one. Here we go. Secant. So for the secant, we're going to use the skeleton of the cosine graph and do the same exact thing that we did before. So cosine starts at 0, 1, comes down at half a pi. At pi, we're at -1, 3/2 pi. At 2, we're at 1. So like this. So then our intercepts, our vertical asymptotes, occur at those roots, so at our x-intercepts. So here, yeah, it's probably not one of those right there. Get rid of that. And then you just do the same thing. Make your quadratic parts. I shouldn't really say quadratic. Parabolic part graphs. It's not specifically a quadratic graph. There. Okay, so my domain, all x's excluding our half pi's plus or minus pi k, where k is in the integers. My range is -infinity to -1, union 1 to infinity. My period is 2 pi. Again, we'll ignore the key points. We already got that down. We are discontinuous. We are symmetric to the y-axis in the middle there, so it's even. And my asymptote is where cosine of x is equal to 0. All right, we did it, guys. We made it. Hopefully you survived. That was a lot. And I will see you guys next time. Goodbye.